Okay, I've been gone for a little bit. I do apologize. Working on non-electronics related projects down here in the basement. But I do have a few pieces of test equipment that I actually need to get working. One for a club demonstration a month or two away, but that's not important. Today I wanted to look at this neat little piece of equipment that I picked up at an auto swap meet of all places. It was $10. It looked cool. It's got something to do with crystals, and I said, yeah, what the hell? That was just too neat to pass up. I think, $10, sure, too neat. This little fella is a Monitor Products Crystaliner, which from looking at the controls, you've got attenuate over here, you've got modulate, you've got a crystal socket, you've got a dial that's got various numbers on it, like 175, 262. Oh, hey, look, there's 455 and 465. Those are familiar. And then you've got 600, 1400, 1500, 17, and yeah, these all seem all look like frequencies you'd normally use with an AM set. When I initially got it, I looked at it and said, well, it's got a modulate switch, it's got what looks like some sort of a volume control, and it's got a jack and a cable. So this must be some sort of transmitting device, like maybe you outputs an AM waveform and you can modulate a signal, except that didn't make sense because it's only got a crystal jack and this singular connection on the front, which I haven't actually identified. This is probably some sort of older Amphenol style connection. Either way, I was stumped until I got it home because it doesn't weigh much, and I have already done the work to get this up and running, so we won't really be piddling around underneath it because there's not much to it. The Crystaliner is actually a fixed frequency test oscillator for aligning AM radios. And it has an external crystal slot on the front, but the selling point of this is that every one of these frequencies seen on the dial here is a crystal mounted inside of a giant Ferris wheel on the back of this knob, so that you can select a fixed frequency, any of the ones listed on there, or an external one. In fact, there's even a blank one right here, and you can swap them out at will, so long as you have the right type of crystal. These crystals actually have pins the same size as octal tubes. So there's only specific types of crystal you could use unless you made an adapter for it. But it does mean that what you have is a selection of very stable outputs to choose from for doing alignment work. So 455 and 465 were the two biggest, most common IF frequencies to deal with. And then if you need to do any of the standard RF alignment, you have 600, that's basically the low end of the band. You've got 1500, that's typically one of the high-end settings they have when you're doing the tracking settings. And you've got 1000, a nice round even number. Generally not any stations there. At least there are most places that there is where I am, so it doesn't do much good. The external setting, and then of course you've got the wild card in there so you could put in some other random crystals. Now what's interesting is what's going on inside. Now there's some other frequencies here that at first seem kind of funky. So you have 175, 262, and 370, which I was a little bit, I wasn't sure what they were doing with those. But it makes a little bit more sense when we go in there. Now I would like to point out that there were a number of different variants of the Crystaliner. They, I want to say, started making them after World War II. Just after World War II, like late 40s, early 50s. I'll have to double check the Radio Museum listing. And they changed year after year, so some of the features were different. So initially, you only had a pair of switches on attenuate and modulate. There was no volume control. In fact, I'm pretty certain this is somebody else's inclusion, because originally there was just an on-off switch here and an on-off switch here. So the attenuate is actually the power switch. And from looking at some photos of other Crystaliners, I'm honestly not sure why they even bothered putting the word attenuate there, because it's not changing the signal level, it's just going from device active to device not active. Whatever. The other switch, the modulate, is actually for an internal 400 Hz crystal-controlled oscillator for a test tone. Because obviously, if you're going to be doing IF alignment, you need a test tone to work with. I mean, well, okay, do you? Well, if you're doing it by ear, which a lot of people are, or if you're measuring the audio output on the anyway, yeah, okay, it is pretty helpful. Either way, not much to it, and I'm going to grab a screwdriver and pop this thing apart. I already took the liberty of, well, fixing it for one, and only putting 2 screws on it to keep it together, so I didn't have to mess around with it much. Now, the test lead that this came with is a very simple affair. It's just an alligator clip on one end of a piece of coaxial cable and a matching connector to this, which I'm glad it came with it because I would have had to have swapped it out, and I don't like doing that on equipment, especially oddball stuff like this. So this is the RF connector it uses. Maybe someone out there knows what type of Amphenol connector that was, or maybe Switchcraft. Now, I've had to repair this. This end was all kinds of screwed up. Same thing with this one. Tore them apart. I put a new alligator clip on here. Heat shrunk both ends, so that's all nice and back together. This has a new power cord. However, there was a somewhat different modification they had to make to this in order to get it properly working. Okay, so if we flip around our chassis here, we can see we actually have 4 tubes in here. And, well, if I turn it from the side, give you a better idea. Here is our Ferris wheel of crystals. Very simple, it's entirely mechanical, and each one is brought into contact with a pair of brass contacts. One at the lower here and one at the top, and there's just a block of either wood or Bakelite holding them apart. Really, 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 really simple. And they're retained by just a nut and a plate on the end of it, and each one of these is labeled with its frequency on there. These are all original crystals too. They all say monitor on them, which is nice. So this is our set of fixed crystals, and here's one outlier. This is somebody else's, and there's the slot with it for external. You could actually put a crystal in there and have an internal one in the external position, so 2 free slots, I guess. But who knows? Oh yeah, and someone did also replace this one, but not important. That's one of the other frequencies that doesn't get typically used for AM alignments. So all 4 of these tubes back here are 6J5s. So nothing crazy going on. So the first 6J5 is being used as a rectifier. I don't remember if it's tied with both plates in parallel. I want to say it is technically a half wave. And then you have 3 separate oscillators. One of these is for the 400 Hz test tone. One of these is for whichever crystal you've selected, and then the other, the last one, is actually for I want to say it's a 7 megahertz crystal, which I believe, yeah, no, that's the modulate crystal. This is the 400 Hz test tone. This guy, over here, that's marked reference. This is about 7 megs, and this is the main oscillator. So when the thing is on, this is going, and B plus is cut off from the modulate. When you select one of these crystals, or your external, or whatever, the oscillator that is hooked up to this crystal is beat against the 7 megahertz crystal and then output. And I read from a description of this what they were doing with that. And I couldn't quite figure out why on earth you would need a 7 megahertz oscillator to be beat against the one that you're using here. Wouldn't you want this? The reason for that actually is because if you wanted to do things like police band or shortwave especially, these frequencies up here are basically useless. However, the original instructions for this thing, which I found a picture of them some time ago on some random obsolete web page, someone had a sheet that was included. There was a table of all the crystals that were included with the device and the frequency, the beat frequency you would get from combining this with the 7 megahertz. Now, if you're setting this to 455 or 465, you're going to get a beat frequency from the 7 meg as well as the 465 or whatever you're using. But when you're aligning an AM set, those really high frequencies, the megahertz range, aren't going to mess with it. So there's no big deal. When you're aligning for shortwave, you check the chart and say, okay, the 455 and the 7 megahertz will produce X signal, and that's useful for tuning tracking. So those other goofy values on the front that don't seem readily useful are useful in some way or fashion for dealing with shortwave alignment when you use the beat frequency from the 7 megahertz plus that. I'm sure I could yank this out of there and not even worry about it, but you know, it's there. I'm leaving it like it is. So here is the underside of the monitor, and it's honestly pretty simple. There are 3 identical oscillator circuits in here, each crystal controlled. We've got this guy over here, which is our tone. We've got this guy over here, which is our 7 megahertz crystal, our beat frequency. We've got the 6J5 that acts as our rectifier tube here. And then this guy right here, which is the whatever crystal you've selected from the front or the external, that oscillator there. Each oscillator also has a radio frequency choke in the B+ line. And there are, I want to say 47 kilo ohm resistors. I actually made a digital schematic for this in Express SCH. I'll put that up in the screen here soon. If you wanted to, you could probably knock one of these things out using spare parts if you wanted your own crystal-controlled RF source, really. It's pretty simple. There's one electrolytic, I think it was a 20 microfarad. I went with the 22, closest nominal value. About 160 volt rated, a 0.1 going from the negative supply to chassis here because it's not a grounded thing. I'm not using a safety cap because, again, there's no ground. It's not going back to the line. Not really worried about that. And then all the major capacitors in here are ceramic. So these guys right here, in mine, these are all the same value, about 10 picofarads. Well, actually, no, sorry. These 3 here are 10 picofarads. This one on the output is 50 picofarads. Looking at other people that have these units, it seems that the values for these parts changed a little bit depending on when they made it. So there are variations on that. One of the biggest ones in this case is what appears to be a user-installed volume potentiometer and switch, which I actually like because this at least allows you some amount of control over the signal strength for the output, because especially when you're dealing with sets that have automatic gain control in them, which most 30 sets do, you want to be able to set this low enough that it doesn't overdrive that, especially if you're not clamping the AGC down to nothing. I typically don't screw around with it. I usually just do exactly what the instructions say, crank it down until you can just barely hear it and where it's not messing with the signal, and you're golden. But in the originals, from what I can tell, they just had a power switch. I don't even think there was any real way to reduce the signal. But so, again, nice little feature, pretty simple installation. Now, the power supply is the biggest thing I had to deal with on this. This is a series strung filament setup, and it originally had a resistance line cord. So resistance line cords were used in like AC/DC sets where the total filament voltage of all the tubes was not equivalent to the line voltage. So you couldn't drop all 110, 120 volts RMS across the tubes. So you had, 10, 20, 30, 40 extra volts that had to go somewhere. Easy solution at the time was to put a power cord that has 3 conductors, a neutral, a hot, and a additional element, basically a very long, flexible, resistive wire that was sized to dissipate the remaining voltage as heat. It's reason why they call them curtain burners is because over time, the freaking cord that gets hot may actually catch fire, especially if you were to damage it. So you'll encounter older 20s, mostly mantle radios, small sets, some all-American early 5-tube sets that have like 25 volt rectifiers or similar. So transformerless midget sets, basically, you'll find might have those in there. The problem comes when you have to actually replace it. So you can't get new resistance line cords, and you wouldn't want to anyways. It's just too much of a risk dealing with that sort of crap. The solution has to be on the inside of the set. I mean, I suppose you could make an external power supply and have a blob or something outside the radio, but that just kind of looks hideous, especially if you have to hide it or if you're trying to sell it and they're trying to explain what that amalgamation on the outside is even doing. So as you can see, I just have a standard extension cord with the female end lopped off and run in. The hot side is going straight to the plates of the 6J5 here to act as the rectifier. This bus bar also connects through this 33 ohm 10 watt wire wound resistor, goes through a 6.8 microfarad film capacitor before going to the power switch. And the power switch on this just operates the filament connection. So it just goes into here, and then it hops over through this bus bar to this chicks, and then so on and so forth, and comes all the way back around to the negative bus, which is connected to the neutral, and then back out to the outside world. The thing with replacing line cord is there are several options. The first, and the one that I've heard people do the most on the monitors, is actually to just get a small power transformer for 6.3 volts, 300 milliamp tubes. Not very hard to find one of those. And preferably something that also has a secondary winding in the neighborhood of about 120 volts AC. Again, not super hard. I think Heathkit actually used some similarly sized transformers for some of their smaller pieces of test equipment. I think I actually have one or two that might have that sort of thing. Or if you have like a junk vacuum tube voltmeter, that probably has a transformer about the right size in it. The problem with that is space. There's not a lot of space on the top of this, and some of the pictures I've seen of ones that were altered when they were still in use involved cutting holes in the back plate, making room for the thing to fit, or even I think maybe mounting it on the outside and running the wires through a hole. Kind of cheesy looking. But that is definitely an option. That would require, however, that all these tubes be rewired for parallel filament operation rather than series. Which, that's not super hard, but again, still you have to modify the original circuit, and it's kind of annoying. Second option would be a diode dropper. So you'd put like a 1N4007 in there and then add in a dropping resistor appropriately sized to dissipate the remaining voltage's heat. But for that, you have to kind of do trial and error, because you can't just assume that the diode is going to cut the RMS value clean in half. It's not. You're actually going to see the peak voltage of that AC waveform, which, from what I understand, a 120 volt AC RMS input has a peak voltage of somewhere in the neighborhood of 169 volts. So if you're putting in a diode in order to power these tubes, when the wave reaches its peak and you have it, you're putting somewhere in the neighborhood of 85 some odd volts across the filaments, minus whatever you're dropping across the resistor, which you can still do that. You just have to make sure that this resistor is big enough to dump the additional, to drop the additional voltage needed to run these. And with the diode dropper, that may mean you're dropping, let's see, this is going to be about 25 volts. You're going to be dropping about 60 volts across this at 300 milliamps. That's probably going to be a fair amount of heat, and you may have to mount it above the chassis. You never know. Honestly, the best option, which is what I went with, is to use a capacitive dropper, because the heat dissipation typically is practically nothing. Now, if I just use a capacitor, it would have been completely nothing. However, the recommendation from all the sources I saw online when I was researching how to do this basically said it's not a bad idea to put a low value resistor in line with the capacitor, probably so that the charge time is lower. Capacitors have an exponential charge rate. You put and that's based on the resistance to the circuit that it's charging from. So having one of these in there means this thing isn't going to try drawing a crap load of current on startup, because all these tubes cold are going to have a substantially lower resistance value than when they're warmed up and drawing 300 milliamps and have a 6.3 volt drop across them. So this is in there to kind of give this guy a break. But more importantly, how did I actually size these? Well, my initial attempt at doing this was the stupid way, which was just to try calculating the capacitive reactance necessary to drop the difference between 120 and the 25 necessary for that. So I thought, okay, I need to drop about 95 volts at 60 hertz, and I think I came with somewhere in the neighborhood of 10 microfarads or something along those lines. So I just pulled the 10 microfarad electrolytic capacitor out of my box without thinking and stuck it in there. And it got extremely hot because you should never ever use an electrolytic cap, especially a polarized one, in an AC circuit. They're just not designed for that. They will probably blow up. If I'd left it in there long enough, it probably would have exploded in my face. Glad I didn't do that for very long anyway. I have seen some people say that you can use non-polarized electrolytics because those have, electrolytics are typically the caps that have the highest values. When you're dealing with circuits like this, you're going to be needing, 6, 7, 8, maybe 10 microfarads. Most, what you would really want to use are film caps. Film caps like these guys traditionally are going to be below the 1-2 microfarad level. You're going to be in the tenths or lower range. Trouble with the electrolytics, again, is you got to find a non-polarized one. Those are typically found in like audio bypass circuits for tweeters. Not so much found for stuff like this, and finding one rated to be able to deal with this kind of line voltage might be kind of hard. The general recommendation was, if you're going to do this, go for a film cap, and more importantly, go for either a motor run or a motor start cap, because those are already designed for heavy use. So in this case, this one's 250 volt AC rated. It's intended for use with an AC motor at line voltage, and they come in relatively large standard values. So 4.7, 6.8, 3.3, those sort of things. So I will say these aren't incredibly cheap. You're probably going to be spending maybe $10 or less, somewhere in that neighborhood for some of these. I bought 2 just in case. And finding ones that were not the can style was a bit of a pain. I was eventually able to locate these on Mauser. Let me grab the bag here so if anyone wants... Oh, well, fortunately I don't have a part number for this. But if I can get this to pick up on camera, if you want to look this number up, come on lighting, work with me. If you want to look that number up, this is the 6.8 that I am using, and it is working very well. So either way, film cap, highly recommended. The resistor here, not entirely required, but seems like a good idea to give this thing a slow start on current. It does dissipate some heat, but I've got it towards the outside edge of the cabinet, further away from all the other components. Seems to be doing all right. So that's more or less it for the underside. Oh, I guess I should mention how I actually calculated this. I kind of cheated. The first website I came to, the guy had already done an example calculation using 4 6J5s with a 300 milliamp drop, and he'd calculated a 33 ohm resistor and about a 6.9 microfarad capacitor would be the ideal choice. 6.9 is not a standard value, so I went with 6.8. And at 120 volts on my Variac, I am seeing about 6 volts drop across each tube filament. So that seemed pretty good to me. But you do have to do a tiny bit of algebra in order to figure this out, because unfortunately, like I tried doing initially, just using capacitive reactance equations to determine what the effective resistance of this cap is don't work because of the, and I'm struggling to remember my work with phasors and vectors here. Capacitors and inductors behave differently in AC than they do in DC, and you have differences in how quickly things happen. So a change in voltage or current across a resistive element is generally instant. A change like that in something like a capacitor or an inductor, there's a lag. So we have to account for the fact that there's about a 90-degree shift in the voltage, I believe. with respect to these. So if I'm summing up all the resistance values of these tubes in conjunction with this resistor right here, and then I am trying to add the capacitive reactance of this to it to get a total resistance that'll drop 120 volts at 300 milliamps, I need to account for the fact that this is not going to be in phase with the rest of that. So the voltage across this, if I assume that these are dropping, I would say 30 volts, I can't just assume that this is going to be dropping 90 at that point, because it's a capacitor. It may actually have a higher voltage across it than you would expect at that instance. So you actually have to use the Pythagorean theorem to calculate it. Basically a right triangle with one 90-degree corner. So you have capacitive reactance and the total resistance and the line voltage. They're all squared. And I'll post links to the websites I got the information from if you want to look at how to do it. It's very simple. It's one of those things that's very handy to know and good to practice. I've been out of practice with that sort of mathematics for a while because I don't typically use it in my day-to-day work. That being said, this works out great, and I want to get it flipped over. I want to button this thing back together because I want to see what the output looks like now. Okay, now we're going to take a look and see what the output is directly out of the jack and the test lead here. I'm going to set this little guy at 455, and honestly I don't know if the modulate switch is currently in the on or off position. I want to say that's off, and we're going to crack this and let it warm up for a second. I think there's something there. Oh, alright, yes, there is definitely something there. So that the attenuation definitely works. So let's crank that up and see if we can't lock in on the sweep here. Can't be traveling too fast for this thing. Oh, I just realized it might actually be a little difficult to get a proper look at this because I'll be seeing the 455 kilohertz signal beat with the 7 megahertz signal. So that's probably why what I'm looking at is kind of messy. Ever so slightly. It looks like it wants to lock every now and then. What I'm curious though is I can see these outer edges here. I want to know what the inner ones are. Do those inner ones change at all? Okay, so that just moved over to 465. See, that one's set to external, so nothing in there right now. Okay, so with no crystal, what I'm seeing right here should just be the 7 megahertz output. Okay, so yeah, so I got the 7 megahertz in there, and if I provide it with... Oops, that's a different crystal. Yeah. Oh, interesting. We can at least see something there. That's the 1000 kilohertz crystal. So it looks like the wider portion we're looking at here is going to be the crystal we've selected, and that slimmer portion is going to be our initial 7 megahertz signal. Okay, so we can see them both. It's not quite as fanciful as I thought. Let's set it back to 455. And let's turn on the modulation. Alright, we have modulation. It actually looks pretty good. Cool. So let's see, 465. That's 1400, 1500. Yeah, alright, so very cool. I think we need a radio to try this with. So I went back through my shelving and I found something that I still haven't finished since, I want to say, college. I got partway through cleaning up the cabinet, and I already redid the chassis of this little Firestone. But I couldn't find the chemical at the time that would really tank this nasty paint off, and I hadn't decided what I was going to paint it back to. But the chassis is all electrically done, so optimal candidate for this, and it'll get me off my butt so I can repaint this thing and get it all cleaned up and put back together. But first, I suppose we should make sure that this set does actually do something if we're trying to fiddle with it. It's been a little while since I've turned it on. Yeah, we're going to get a little bit of noise from my LED fixture. Sorry. Okay. So I'm going to find a quiet spot on the dial. Okay, that seems quiet enough. Now, I am just going to lay the cable for this around the back of this thing. I think we should be able to get enough coupling out of it without having to, or here. I'll simply clip the lead on the cardboard next to the loop antenna, and we'll see if that works. Okay, I'm hearing a little bit of a buzz in the speaker that wasn't there before. Let me try some. Yep. Okay, now if we turn on the modulation. Alright, so it is there. However, I don't actually know if this one's set up for 455 or 465 specifically. That being said, let's see if the other frequencies are about where they should be. So let's try 600. Turn this down while I do that. Okay, so it's a little somewhere between 6 and 550 on this band. I'm willing to bet that this is a little more accurate than this, being that it's crystal controlled instead of a typical tank circuit. This dial was just made out of paper, and I'm sure it was graduated somewhat generously. Okay, so that's about where it ought to be. Let's try 1400. So that one's showing up a little below 1400, more like, I don't know, 13? Okay, let's try 15. Okay, 15 is a little further up here. The tracking on this may be off. I never touched it, so... And 1700. Yeah, we're getting that up here. And just for clarification, 1000, which should overlap with KOMO. Yeah, see, it's overlapping with the station right there. Let's turn off the modulation and crank this down and see if we can just hear the station there.
Reversing hair loss is life-changing for me, and some of you have asked, so what? They are a strong local contributor impacting thousands.
Okay. So I would say that this does work, although out of curiosity...
Anywhere, their advanced FUE treatment is simple. It takes just one visit, and your own natural hair begins to regrow the
What happens if we switch over to external? So now it's just a 7 megahertz. We shouldn't hear anything.
Public. So this is a very useful thing.
Yep, can't hear anything. Modulation on or off when it's in the external position, so that's good. So I would say, honestly, that about does it. Looks like it'll be a handy little piece of equipment. I might take it to work and try it on our digital scope and see if the outputs from the crystals are what they say they are. I mean, I would assume a slice of quartz wouldn't change too much, but you never know. But that about wraps it up for this video. Just wanted to get another little piece of vintage test gear working for my bench, because frankly I love having stuff like this. And this particular unit really stuck out to me just because of the styling. The nickel, or probably nickel, on here with the red bars. Just the red bakelite grip with the chrome, with the trim strip over the top of it. Just very, it has a lot of sex appeal if you're putting it on a bench. And I'm moving towards a lot of my equipment being less utilitarian and more machine age design looking, because that's really one of the big things that I love about equipment from that era, is that they actually put style into it. Yeah, functionality is important too, but it's got style. Anyway, thanks for watching, and I will have this video come together here somewhat soon about another piece of equipment that I'm actually going to be demoing at a radio club meeting. And I need to have it done before September, so looking forward to that. Thanks again for watching.